Hey there, chemistry. So, unit 6 here is about what's called stoichiometry. Okay, it's a big weird word, right? Stoichiometry. What stoichiometry is it is a mathematical process where we can take a look at the relationships between the amounts of reactants and products in a reaction. So, we could answer questions like, let's say I start off with 100 grams of this chemical and 100 grams of that chemical, and they react, and they're going to produce some third chemical. How much of that third chemical is going to be produced? I mean, we can make those kinds of predictions, which is important for people, especially people who work in like a chemical factory, a chemical plant, and they make, I don't know, artificial flavoring or something, or they make gasoline or something through some kind of chemical process, because they need to be able to know, predict how much of the chemical they're going to produce, right? So it's an important thing. Stoichiometry can also help in other parts of life. I'm sure everybody has seen the kinds of problems that ask you to take some numbers and they ask you a question, right? And I'm sure everybody has sat there and looked at a problem and thought, do I need to multiply here or do I need to divide here? And stoichiometry is a process that can help you set things up. Even if you don't know, do I multiply or divide? It can help you set things up and help you decide whether you multiply or divide. We're going to look at specifically having to do with chemistry, but it can also help you in other areas as well. To that end, we're going to spend the whole unit learning about stoichiometry. This first lesson, we're going to do the very simplest part of stoichiometry. But to do that, we first need to talk about how we measure how much of a chemical is reacted or produced. And so today we are going to talk about what's called the mole. And our target will be to be able to solve mole problems, which will make more sense when we're done talking about them. Okay, so in chemistry here, we need a way to talk about how much of a substance is reacted or produced, how much of it takes part in a chemical reaction. Now, we can take a substance and measure it on a scale and talk about how much there was in grams. That's something we can do. We can talk about how much in grams. And we will talk about how much in grams next time. This time, though, I want to explain why that isn't quite good enough. Okay, I'm sure everybody's probably heard, I don't know if it's a joke or a riddle, somebody probably told you when you were a kid. They'd ask you, which one weighs more, a pound of feathers or a pound of lead? And kind of the joke or the riddle is that, a lot of people in their heads would really quickly say, oh, the lead is going to weigh more because lead is a lot heavier than feathers. But then, you got to step back for a minute and understand that, well, it was a pound of each one, so they weighed the same, right? And that's kind of the idea why talking about our substances in grams is not sufficient here, okay? So think about the lead and the feathers, right? Lead is more dense than the feathers, so a pound of feathers is going to be a whole lot more stuff than a pound of lead, right? And that's why you jump to this in your mind that the lead would be heavier, but even though they weigh the same. So think about our chemicals, right? I'll tell you, a carbon atom weighs 12 times as much as a hydrogen atom. So if I were to put a carbon atom and a hydrogen atom on scales, I would see the carbon atom weigh 12 times as much. So if I had equal amounts, the same number of grams of carbon and hydrogen, well, then I would have 12 times as many hydrogen atoms as I would carbon atoms, right? So sometimes it's not so much about how much they weigh, it's about how many atoms there are, okay? And this is where we get into this idea of the mole. Okay, now step back for a minute. We have the mole is a way of counting atoms. Okay, you say counting atoms, That's ridiculous. Even in the tiniest drop of water, you've got trillions and trillions and trillions of atoms, right? But when we count atoms, we don't really count them individually. We count them in groups. Okay, think about how people count eggs. People don't count eggs individually, they count them in dozens, right? We have a word that stands for a number there, a dozen. A dozen is 12, right? And we have other words that stand for numbers. You might buy something in a gross. A gross is 144, it's 12 dozen, right? You've heard Abraham Lincoln said 7 years ago. What is a score? A score is 20, right? So 4 score is 80 and 7 is 87, right? So we have these words that stand for numbers, right? And in chemistry, we have one of these words that stands for numbers, and it is called a mole. Not that kind of mole. Not that kind of mole. That kind of mole, right? A mole stands for a number. A mole is this many. That many is a mole, and that is a lot. That is a whole lot. That is that many. So that many, that is a huge number. That is a number that's so big we don't have a name for it, which is why we just kind of write it in scientific notation here, right? A mole is this many. And this is why we use such a huge number to count atoms, because there are a huge number of atoms. This many is called a mole, just like 12 is called a dozen, right? So this is a mole. Oftentimes we will abbreviate mole as, don't ask me why we do this, okay? We're going to abbreviate this 4-letter word as mole. 3 letters. I don't know. It's just what we do, okay? We abbreviate mole as mole. Okay. Now this number, this is a special number. This is called Avogadro's number. Named after the famous scientist Amadeo Avogadro. And there's some funny memes about Avogadro. You can see the picture of him. He looks a little smarmy. And then, this is called Avogadro's number. So maybe, ladies, you want to take Avogadro's number. Okay. Yeah, so that many in a mole. So when we talk about atoms and molecules, there are this many in a mole. So if I say a mole of oxygen, I'm talking about this many oxygen atoms. Okay, something to understand when we look at our chemical equations. In our chemical equations, there are coefficients, and those coefficients tell us how many molecules are involved in the reaction. So like in the chemical equation there, you can see it says 2H2. That tells me that there are 2 hydrogen molecules involved in that reaction. Then on the other side, you can see, 2H2O. That tells me that 2 water molecules are produced. And then, of course, the oxygen without a coefficient in front of it, that means that there was only 1 molecule involved. But now these coefficients can tell us something else. Not just how many molecules were involved, but they could also stand for how many moles were involved. Okay, so we could read this and we could say that 2 moles of hydrogen molecules and 1 mole of oxygen molecules produce 2 moles of water molecules. And that's important for us because we're gonna, go forward and we're going to do some math with this. Now, let's go ahead and do that right now. Okay, so my first example that I have here, let's take a look at this example. It says we're going to conduct a reaction. We're going to conduct the reaction with this particular chemical equation. We're going to do this reaction. And let's say that 4 moles of hydrogen reacted in this reaction. How many moles of water would be produced? You can see the problem there. Okay, how do we go about solving this? Well, I'm going to show you now how to set up a stoichiometry problem. Okay, and every single problem we're going to set up, pay close attention to how we set it up. Going forward, the whole unit is we're going to set up problems like this. Okay, so what we're going to do is, first thing that we're going to do when we set up the problems, we're going to look in the problem and we're going to see what is the number that they gave us in the problem. Okay, and we're going to write that number down. We're going to write down the number. We're also going to write down the units and the chemical that it was. Okay, so looking in the problem there, it said 4 moles of H2. So I'm going to write down 4 moles of H2. Okay, put down the number, the unit, and the chemical. Okay, and what we're going to do is we're going to take that number that we started with from the problem and we're going to write it like a fraction. And every single stoichiometry problem we're going to do like this. We're going to write it like a fraction by putting it in the numerator, and in the denominator we're going to put 1, just to make it look like a fraction. And then we're going to write times, and we're going to make another fraction bar. Okay, now this second fraction, what we're going to do to set up this second fraction depends on what we started with. And later on, I'm going to show you a little map that's going to help you decide how to set up the next fraction. Okay, but for these problems today, they're all going to be the same. We're going to look at the chemical equation, and we're going to take coefficients from the chemical equation, and we're going to put them here and here so that we can solve the problem. But how do we know which ones to put here and which ones to put here? Okay, well, when you set up a stoichiometry problem, you are always going to be looking from the top of one fraction to the bottom of the next fraction. Okay, you can see that the unit and the chemical in the top of this fraction has to match up with the unit and the chemical in the bottom of this fraction. So what I'm going to do is I'm going to look up in the chemical equation and I'm going to see how many moles of hydrogen are in that chemical equation. And if you look at that chemical equation, in front of the H2, you see the number 2. That says that there are 2 moles of hydrogen involved in that chemical equation. So here, I'm going to put 2 moles of H2. Okay, so I want to make sure that the unit and the chemical from the top of one fraction match up with the bottom of the next fraction. And then when they match up, they cancel out. So the bottom of the next fraction is usually the easiest one to set up before the top, because it's got to match up. Okay. Now, the top of that fraction, what I'm going to do is I'm going to look at the problem and say, which chemical did they ask me about? Well, in the problem, it asked me about H2O. It said, how many moles of H2O? So I'm going to go into that chemical equation again, and I'm going to look at what's the number in front of H2O. How many moles of H2O were involved? And if you look there, you can see there were 2. So on the top here, I'm going to put 2 moles of H2O. Okay. Now, these should cancel out, and what you're left with right here should be the unit and the chemical that the problem asked you about. Okay. So now the problem asked me how many moles of water. Here I have moles of water. Now, to solve the problem, what we're going to do, so you can always just skip and forget about this 1 here. So we're going to take this number times this number divided by this number. So you want to multiply all the numbers in the top and then divide the numbers in the bottom. So I'm going to do 4 times 2 divided by 2. So that's 8 divided by 2 gives you 4. And then it's for what? We have to put a unit in the chemical. So it's for what It's 4. It's the same unit in chemical that you had right here at the end. It's 4 moles of water. And there is our first stoichiometry problem. Okay, look at another example here. You can see we've got the same chemical equation, and then the question says, if 8 moles of water were produced, how many moles of oxygen reacted? So what we're going to do, just like every stoichiometry problem, we're going to always start with the number they gave us. So I look at the problem, it says 8 moles of water. So I'm going to write 8 moles of water. And then, of course, we're going to write that like a fraction by putting it over 1. Okay. Then times, it's always times. And then to set up the next fraction, we're going to look at that chemical equation again. Okay. On the bottom, I want to match the top. The top said moles of water. So let me look at that chemical equation and see how many moles of water were in the equation. And there were 2 moles of water in the equation. So down here on the bottom, two moles of water. So I'm going to cancel this one out with this one because they match up. And then in the top, I want to put how many moles of what they asked us about. And the question asked us how many moles of oxygen. So looking in that chemical equation, how many moles of oxygen? Well, there's no number in front of the oxygen, which means it was 1. 1 mole of oxygen. Okay. Now let me make sure that what I have here is what the problem asked me for. The problem asked me for how many moles of oxygen. Now I have moles of oxygen. So let's work out the math. I'm going to do 8 times 1 divided by 2. 8 times 1 is 8, divided by 2 will be 4. So the answer to the question is 4 moles of oxygen. And that's all there is to it. Okay, have a look at one final example here. This one involves a different chemical equation. You see this chemical equation says 4NH3 plus 3O2 reacts to form 2N2 plus 6H2O. And then the question says if 7 moles of oxygen react, how many moles of nitrogen will be produced? Okay. So just like every problem, what we're going to do is we're going to start with the number they gave us in the problem. In the problem that said 7 moles of oxygen. And just like every number we start with, we're going to put it in the top of a fraction, put it over 1. It's always times. Now, for the next fraction, we'll look at that chemical equation. And we'll say, okay, in the bottom, I need moles of oxygen. How many moles of oxygen? Let me look in that chemical equation. There were 3. So I'm going to write 3 moles of oxygen. And then because my units match up here and down here, I'm going to cancel those out. In the top, I want to know how many moles of what the question asked me about. So look in the question, it said how many moles of nitrogen. So in my chemical equation, how many moles of nitrogen? What was the number in front of the nitrogen? It was a 2. So in the top here, I will put 2 moles of nitrogen. Okay, and then we could go ahead and work out the math. We've got 7 times 2 divided by 3. Let's see, that's 14 divided by 3, which should be, let me get a calculator. About 4.7. 4.7, and it's 4.7 what? It's 4.7 moles of nitrogen. And there we are. Okay, so these problems that we just looked at are pretty simple. They are just 2 fractions long. And the problems that you're going to look at on your assignment are also just that simple. They're 2 fractions long. We will eventually, by the end of the unit, get into much longer problems. We're going to see problems that are 5, 6, 7 fractions long. A lot more involved. But along the way, I am going to show you a map that will help you predict exactly how to set up the problem, and it won't be any issue if you know how to follow the map. And I will show you the map next time when we learn about grams. So until then, hopefully we're now able to solve these mole problems, and yeah, take it easy.